Back in chapter 5, we were looking at discrete probability distributions where there are only so many outcomes for each trial. And then when we got to section 5.3, we were told, hey, you can use means and standard deviations and z-scores to decide whether something's unusual, rather than finding the 5%, whether it's less than 5, probability is less than 5%. So why? But notice these conditions that have to be met in order for this to work. Well, the n times the probability of success has to be bigger than 5, and n sample number of trials times the number of failures, probability of failures also has to be bigger than 5. And people ask why. Well, I've got this little calculator that I pointed you folks to last week. I don't know if you used it. You didn't need to use it. And I had it say, okay, here's the number of trials, 130, and here's the probability of success. And if we graph all those probabilities, it gets this nice smooth normal curve. Okay, so because it's that nice smooth normal curve, we can use the mean and standard deviation. Okay, so notice they do give that to us here. So the mean equals 97.5, and the standard deviation is 4.937. Okay, so we'll hold on that, remember that. Now, what happens if it's that n times p ID is not bigger than 5? So I dropped this number of trials down to 13. 13 times 0.75 is, I think it's 9.75. So that's bigger than 5. But when we do 13 times 0.25, remember the failure, that's only 3 point, that's only, I didn't do it. 13 times 0.25 times, oh, no, I don't have time. That's only 3.25, and see, that's not bigger than 5. So that tells us this is not a nice normal distribution. In fact, it's left skewed. Okay, so we can't use the mean and standard deviation to do much with this. We'd have to resort to a binomial probability calculator or the table or the formula. Okay, so that is that. Now I have this. Now, one thing I should do, I'd be remiss in this video if I didn't talk about this. How do I calculate the mean and the standard deviation without this slick calculator? Well, to find the mean of a binomial distribution, we're going to do n times p, which we already did with this calculation over here. Well, that was 13. So if we make it 130, it'll become the 97.5, right? So 130 times 0.75 is the 97.5. And then to get the standard deviation for a binomial distribution, it's n times p times 1 minus p, or q. And notice how n times p is n times p, which has to be 97.5. And then we do times n minus p, or 1 minus p, so 1 minus 0.75 is 0.25. We're going to multiply that and take the square root of it. Let's see. And I did that earlier, and I got 1. No, I didn't get that. I got 97.5 times 0.25 raised to the 0.5. That's taking the square root. Something's not right. 97.5 times 0.25. Then I'm going to take the square root of that. 4.937. There we go. I got him now. Okay, now then it says if we go look at the problem, we see that we're trying to see if having only 85 people survive is an unusual result. So we can use a z-score, and the number we're interested in is 85 minus the mean divided by that standard deviation. So it's negative 12.5 on top divided by the 4.937. I'm getting a z-score of negative 2.53. So this is more than two, so 85 is more than 2 standard deviations below the mean. So that's an unusual result because the rule of thumb we used earlier chapters was if it was more than two away from the mean, more two standard deviations away from the mean, it was unusual. So yes, this is unusual. So this is how it works for those discrete probability distributions. Okay. And then we're moving on to chapter 6 now, and then we talk about strictly normal distributions. Now these are continuous random variables. That means it can take on many different values. Okay, um, and then if we're going to look for probabilities associated, rather than using z-scores, we can actually find probabilities because it's a normal curve, and you can go watch look at Dr. Stevens' work on these problems because he's got the asterisks with him. You can also in Canvas in week 7 overview, I've got and then click on my normal curve calculations with an applet or something like that. And I walk you through these two things with that David Lane applet. Go watch it. I'd rather you do the applet than try to struggle through with the tables and everything. You certainly can. It's not wrong to. Dr. Stevens walks you through the table. So, you certainly can do that if you want to, but it's nothing wrong with using shortcuts like an applet. Okay? And then, how does it work when we're dealing with things that aren't on the standard normal curve? Here, let me delete this. And I pulled off, I wanted to look at this problem here. Since you've got the answer, you can go see Dr. Stevens' method with the z-scores and z-score table, but you can also use this David Lane applet, and I've got links to it it's a normal CDF applet, it's called. You can also just Google David Lane normal. Make sure you add the normal to it because David Lane was a white supremacist, not a very nice man, and he died in prison. I don't know, a few years ago now, I guess. So you don't want to read about him, but you do want this calculator. And the beautiful thing about this calculator, if you watch my other video about using this for the standard normal curve, like questions 1 and 2, this will let you get probabilities without having to find a z-score. All you've got to tell it the mean, tell it the standard deviation, and then what you're looking for. So on a certain stretch of highway, they tell us it's normally distributed, so we're good to go with this calculator. They're telling us the mean is 70 miles per hour and the standard deviation is 4. So you go find that David Lane calculator, David Lane normal calculator. Here, let me get rid of this. Can I delete this? Oh, let's delete this. Can I delete it? Yes, I can. And what you set up is you say value for area from a value. Area is a probability. And we want to know what percentage of cars are traveling faster than you. So I put in the mean, I put in the standard deviation, and I want to know above, faster than me. I'm traveling at 76, it says, right? What percent of cars are traveling faster than my 76? So this area here. Here's where I'm traveling. What percent of cars go faster than that? And that's the answer, without having to find a z-score. I mean, you certainly go, if you did it with z-scores, you would do z equals, and Dr. Stevens did this, 76 minus 70 divided by 4, that would be what, 6, so 1.5, and then we'd have to look in the table in Dr. Stevens' book, and Dr. Stevens, which is in the back of the book, his table would tell us this area. To get that black area, we'd have to do 1 minus that answer from the table. See how the applet is so much easier. You just can decide it is not cheating. You're still having to do that same understanding. Okay, and then the last part, and while I'm doing number 7, I might as well finish it for you. You have time only to get 1 out of 50 cars, so that probability is 2%. So to use the David Lane's applet for this, notice we know the percent, we don't know how fast they should be traveling, that's the X value. So we changed the radio button to value from an area because we've got the area. We know it's 2%. And when that happens, you get the place to type in the area, you put in the mean, you put in the standard deviation, and then it just calculates it for you. So you're not going to pull anybody over that's going uh, slower than 78.12 or 0.215 miles per hour. I'm not speaking for all state police, but or town constables or county sheriffs, but a lady here where I work was married to a trooper, and that person always said he never pulled anybody over on traveling less than 80. So that's in the ballpark. Probably why. That's probably why. Okay, so that's using David Lane's applet rather than Z-scores. So I hope that helps. You go watch my other videos there.